In heavy civil construction, rework consumes an average of 5% of total project costs. Fixing a grade mistake, while the site is still raw dirt, costs a machine pass and a few minutes of time. Fixing that exact same elevation error after the pipe is bedded, the gravel is compacted, and the concrete or asphalt is poured means tearing out finished infrastructure and building it twice. Modern sites often operate under a technological assumption. When a fleet is fully equipped with GPS and machine control monitors, it creates a false sense of security regarding millimeter-perfect execution automatically. Relying on that high-speed technology without understanding the mathematical limits of the hardware creates invisible, creeping errors. By the time those errors are discovered by an inspector, the project margins are already destroyed. GPS and machine control are highly effective tools for horizontal layout. When you need to establish line, the side-to-side alignment of a road or a trench, satellites lock the machine in to within a centimeter or two. But the system has a severe physical constraint. The satellite constellation is entirely above the job site. There are no GPS satellites underground to provide a lower reference point for true 3D triangulation. This diagram illustrates the resulting blind spot. On the horizontal axis, the precision is tight, but on the vertical axis, the lack of a lower reference creates what operators call vertical wobble. The up and down reading is loose, resulting in a 3 to 4 centimeter margin of error on the z-axis. That 4 centimeter wobble is enough to ruin a gravity-fed utility system. A sewer installed on a minimum grade falls only a few hundredths of a foot across an entire stick of pipe. If the GPS vertical error flattens or reverses that grade, you create backfall. The water pools instead of flowing, and the entire run fails inspection. This physical limitation dictates the absolute unbreakable rule of the site. Line, yes; elevation, never. To hold strict vertical tolerances for pipe inverts, finished floors, and tight road slopes, the site cannot rely on a network of satellites. It must depend entirely on deterministic, ground-based geometry. That ground-based geometry begins with the survey stake, the starting anchor that tells the crew exactly how high to build. Look closely at this field mark. Surveyors leave behind two distinct pieces of wood, and confusing them is a critical error. The tall piece of wood with the neon ribbon and the writing is the lath. It is essentially a billboard. The actual mathematical point is the hub, the small, separate stake driven almost completely flush with the dirt directly beneath it. The writing on the lath dictates how the ground must move relative to the top of that flush hub. C means cut, or dig down. F means fill, or build up. These instructions are written strictly in decimal feet. A stake reading C 1.50 means a cut of 1.5 feet, or 1 foot and 6 inches. It does not mean 1 foot and 5 inches. Gradework operates in tenths and hundredths of a foot to maintain precision. If a machine knocks out the hub, the math is gone. Pulling a tape measure from the tall lath instead of indexing off the true flush hub compromises the entire geometric chain. Once you have a valid point on the ground, you have to project that elevation across physical space. This is done using the core concept of field grading, the height of instrument, or HI. To establish an HI, you first need a benchmark. This is an undisputed anchor point left by the surveyors, like an elevation nail in a stake or a mark on a concrete manhole, where the exact elevation above sea level is already known. The operator takes a backsight reading on the benchmark. Adding that distance to the scope establishes the height of instrument, creating a flat horizontal plane floating over the site. Every subsequent measurement is subtracted from this plane. This distance dictates your exact grade. Establishing this plane is the only way to translate a flat two-dimensional profile drawing into a dynamic three-dimensional environment. A grademan who understands how to establish an HI plane off a single benchmark can keep an entire crew producing all day, even if heavy machines destroy the rest of the primary survey stakes. But an HI gives you a perfectly flat plane, and engineering reality dictates that roads are never built perfectly flat. They must be shaped to actively shed water, otherwise pooling will tear the asphalt apart. A road surface is defined by two primary geographic features: the crown, which is the high point running down the center, and the edge of pavement, or EOP, on the outside borders. The road falls from the high crown down to the EOP on both sides. This angle is the cross slope. typically engineered at a 2% grade. It drops about 0.02 of a foot for every foot of distance. Projecting a single, flat, horizontal HI plane from a laser is not enough to build this sloped 3D surface. To hold that exact angled grade across hundreds of feet, the crew needs localized physical controls. This brings us to a lost art in civil earthwork, the boning rod array. It is the ultimate analog failsafe for controlling sloped grades without relying on batteries, screens, or lasers. The system uses 3 T-shaped poles, 2 fixed sight rails, and 1 mobile traveler rod. Because the center crown is higher, the center rod mark is set lower. Aligning these offset rod tops creates an optical sightline running perfectly parallel to the sloped grade. Boning rods convert complex angled cross-slope calculations into a simple, unbreakable optical line. It requires 0 calibration and it cannot run out of power. Modern road design often adds another layer of complexity, the parabolic crown. Instead of a straight, flat slope falling from the center to the edge, the road features a compound curve. To build it accurately, the crew must establish a quarter-crown checkpoint halfway down the slope. Setting the height for a compound curve by eye across boning rods is risky. Instead, crews use a highly tensioned string line, pulled directly from the lip of the concrete curb out to the center crown rod. The math for a parabolic shape dictates that the quarter crown sits exactly at 75% of the total crown height. The Grademan calculates that elevation drop, measures halfway out along the string, and ties a ribbon to lock in the quarter crown position. With the string tightly tensioned across the specific width of the road, the Grademan simply drops a deterministic tape measure directly from the string down to the dirt below to check the exact required depth. Adding the string line to the boning array eliminates any optical guesstimating over a curved surface. It takes a complex mathematical parabola and turns it into a rigid, physical measuring point that anyone on the crew can verify instantly. Beyond reliability, a boning rod setup accelerates the workflow through standardized visual references. Surveyors leave marked elevations at stations every 20 meters. By installing permanent sight rails at these specific points, the setup time is invested once for the duration of the grading pass. From there, the Grademan walks the length of the road with the mobile traveler rod, utilizing what is known as the T-thickness reading trick. Notice in the top scenario, the red traveler aligns perfectly with the sight line. The grade is exact. In the middle scenario, the top of the red traveler sits roughly 1 T-thickness above the sight line. Because the physical wooden top is exactly 1 inch thick, the Grademan knows instantly that the dirt is 1 inch too high. In the bottom scenario, the traveler is 2 T-thicknesses high. The ground requires a 2-inch cut. The Grademan reads the optical thickness, drops the rod, and immediately paints the required cut number, a 1 or a 2, directly onto the dirt in front of the heavy equipment. The T-thickness trick turns complex leveling math into an intuitive visual language. A single Grademan reading analog rods can dictate the precise cutting speed and accuracy of the entire machine fleet without ever waiting for a laser to self-level. Shooting the grade and moving the dirt is only half of the required workflow. The final obligation of the Grademan is entirely administrative, recording the final physical reality of the site. The engineering plan is the promise. The as-built is the proof. An as-built is the formal legal record of the exact elevations, locations, and measurements of what was actually constructed in the dirt. When a manhole is shifted to avoid a conflict or a pipe elevation changes to clear an obstacle, the Grademan immediately executes a red line. They physically cross out the original plan detail, write the new location and elevation in red ink, and date it. Failing to redline a fumed alteration leaves a toxic trap for the future. Years later, repair crews will use the outdated plans to dig blindly for shifted structures, wasting massive amounts of time and money tearing up the wrong ground. The Grademan operates as the critical translation layer between theoretical engineering models and raw earth. They read the math, protect the hubs, establish the physical geometry, and record the truth of what was built. While satellites and lasers can accelerate the workflow, technology alone cannot hold a site to its tolerances. Guaranteeing that the math on the page perfectly matches the dirt on the ground will always require an operator who has mastered the analog geometry of the site.